Right, so today we're just going to keep on going with this interplay between factorizing polynomials and integers with coefficients and integers versus factorizing them with coefficients and rational. And hopefully we'll get to Eisenstein's criterion. This is very useful when you do field theory, but kind of one fact out of it for this class. So let's see where we left off. We left off with Gauss's lemma. I'll read what that said. It just says product primitives primitive polynomials. Primitive. And remember that primitive polynomial is just a polynomial with integer coefficients so that all of them are relatively prime, like collectively, it's a set, and that the leading coefficient is positive. So we want to use this to kind of show that irreducibility with integer polynomials will give us more or less irreducibility of rational perspectives. So we need a few more lemmas. These. So one is sort of a way of breaking down any rational polynomial. So suppose f of x is a rational polynomial with rational coefficients. Say it has positive degree. And then there's a unique rational number and primitive polynomial f naught of x that satisfying this equality that it's just. So the key bit here to keep in mind as we work through this is really this uniqueness. So you'll see that, well, maybe you guys can already guess that indeed this is not defined one such thing, but we want to say that it's unique. Okay. So maybe, yeah, let's start doing that check and make sure we all agree. So why can I find such a factorization? Let's give you a rational polynomial and say, does there exist a rational number and primitive? Okay. So are you saying like clear all the denominators of f, right? Right, okay. Yeah, so you could just, yeah, straight. You can pull all the product of all the denominators factors out, then that will give you an integer polynomial, and then you can kind of find the greatest common divisor of all the coefficients of that integer polynomial, pull that out, and you'll get a primitive. Maybe make it plus or minus 1. So it's certainly not too hard. I mean, think about that for a minute if it moves too fast. But I think that it's not too hard, just basic arithmetic, to say such a factorization exists. I'll just say X set up pretty hard and neat. That's basically what we just said. Why is it unique? Suppose so if we have that we have 2 of these, so let's say we have a C tilde F naught tilde of X. Well, I can certainly bring then divide by C, or maybe multiply by C. This is rational numbers a priori. Look at this equality. So if I call this number R, it's a rational number. What can you tell me about R?
Has to be 1.
Okay, you say R has to be 1, so explain yourself.
Because F tilde and F tilde not of X and F not of X are both primitive polynomials, so they can't have like any common factors you can bring to them.
Okay. Yeah, I think that's more or less right. I mean, what I would say first to get where you are, I think, is okay. F naught is an integer polynomial first. It's integer coefficients. So if R had a denominator, right? Wrote it as like P over Q with their relative. If R had a denominator, then that denominator would have to factor each of the coefficients here. Otherwise, I get a fraction as it's an integer coefficient. So that means that there's some integer that factors all of the coefficients here. But this is primitive. So that doesn't happen. So the denominator of R is 1. But now if R has a numerator that's not 1, then we have a greatest common factor of all of the coefficients here. But that means that the numerators of R is 1. Really, I should have said, when I said both of those things, they should be plus or minus 1. But since the leading coefficients of these are both positive, we actually know it's plus 1. So that's a verbal argument, but hopefully you'll be content with that. Because that R equals 1. Once R equals 1, then we have that these two primitives are the same. And we have these two constants. Multiplying both sides of R equal 1 by C gives us C tilde equals C. Then so that's the unique stuff. Show that there's only one way to do this. That comes in handy with several of these arguments. This fact. All right, so let's use this fact. Here. These are all sort of, there's like the sequence of results, and it's all to build up to this kind of result that Z of X is a UF. That's a unique factorization. Here's a 2 parts. 12.6. Let's let F naught be primitive. Okay. Let G integer polynomial. If we have that F naught divides G U of X, rational. I mean, they're both integer polynomials, or polynomials with integer coefficients, but we can view them as polynomials with rational coefficients. In that world, if we apply it, then we can also do it in sort of, I don't really care about the, I'm just gonna leave it. B is kind of medium. Okay, so let's now in mathematics, frequently when we're doing these kinds of proofs, and often when you're doing exercises, of course, you know, it's helpful to kind of look at the material in the section, right? And to use some of the results. Some of those results get you there. So here's a perfect example of this, where I think we just start trying to prove this from the beginning. It can be complicated, but we have a result. We want to use it. So we're going to assume F naught divides G in this in rational polynomial. So, X have G is equal to F naught times H. But now we want to use, as I just said, we want to use this result we just had, that any rational polynomial can be factored as a rational number times the primitive. So let's use C of G naught, F naught, tilde of H. I can bring that constant out to the front. Polynomials are integers, all commutative. For here, of course, it's E tilde are rational. It's rational numbers. P naught. F naught is already primitive by assumption of the theorem. Already. Not consider our primitive. Say anything?
Well, like Gauss's lemma tells us that F naught times H naught is going to also be primitive.
That's great.
And I think we can use a similar argument.
So Gauss's argument, our lemma says this is lemma says this is and now we don't need to use an argument of the last proof, we actually have a fact in the last lemma, which is that this factorization is unique. Right? We have that whatever G is this, and G is this. And here we have a rational number and a primitive, a rational number and a primitive. That's a unique factorization based on what we just did. So the previous lemma is equal to C tilde. G naught is equal to F naught H naught. Okay. Well, I mean, but G, of course, is equal to C times G naught. Now, because G is an integer polynomial, this is an integer. Integer polynomials, this has to be integer. It's a rational, then we would have a rational. So this is going to equal F naught H. This is then integer C. C is equal to C tilde. Well, because they're all both integers. H naught is an integer polynomial, it's primitive, and C is an integer. So divides E. Question. Okay, we're almost there. One more proposition, and we'll have our. Okay. So let's let F be an integer. Let F be an integer. And let's we call it the leading coefficient is positive. Then F is irreducible in ZX. Only one of two things happens. Either F is a prime number, prime integer. Or F is a positive degree, but it's a primitive polynomial. Irreducible. It's a primitive polynomial. irreducible in okay. So this is a very wordy thing, I would say, but okay. The upshot of it is B, which is just to say what we had in for PIDs before is still true. Every irreducible polynomials with integer coefficients is prime. That's the key. So A is really just kind of a wordy way of getting to. Okay. So but let's start if F is irreducible in Z. Then okay, well, let's split into two cases. If F equals 0 means that F is an integer. It's positive because we assume that F is leading coefficients is positive. So irreducibility in integers, natural numbers, just means you have a prime. Factored into integers, one of them is 1. It's just the definition of prime. Just definition. Okay, so it's 1, 2. F is actually a polynomial, like a positive degree polynomial. And then, well, it's irreducible in ZX. So I'll say it must be primitive. Why is that? Well, it has leading coefficient as positive, so that's one thing. Why is it a primitive? It's a definition check. What does it mean to be primitive? It means that the leading coefficient is positive. That's okay. That there's no integer that divides all the coefficients. What if there was an integer that divided all the coefficients? It would be irreducible. You'd be able to factor that integer out in C of X, and you'd be able to write this product of two things, both of which are not units. So this is just coming from the definition of irreducibility and the definition of primitive. I'll just say for otherwise. F would equal some D time. Well, we could write it in terms of the factorization. F naught. C is an integer. And C. C would be some greatest common divisor of all the coefficients. This would be contradict irreducibility. All right, and why is it irreducible in Q of X? Also, f is equal to g times h in q of x, well, again, you can kind of do this argument we had before, but, well, I guess maybe the way to do this would be the following, is to take this, say this is equal to c times g naught times h, which equals g naught times c of h. In other words, you can make one of these two polynomials an integer polynomial, but then we're back in this previous proposition. We have now that an integer polynomial divides a primitive polynomial divides an integer polynomial. And that means that this is true in Cx as well. We have, so in other words, we're saying by this result, means P naught divides f in Cx, but then that means they're associates. That is irreducible. If that's true in Zx, then it's certainly true in F. Okay, so that's part A, and then part B. Really after. Okay. Let's suppose so. Zx is a domain, an integral domain. So primes are irreducible. That's just generally okay. But we wanted to, just like for PIDs, we wanted the opposite. We wanted to say that if we had an irreducible, that it would be prime as well. And so that's what we're doing here. Let's suppose we have an irreducible. Suppose f is irreducible. Well, then we have part A. Says, okay, if f is in Z itself, it's constant, then it's prime. And last time, we showed that if we have a prime integer and it divides two integer polynomials, a product of two integer polynomials, then it will divide one. That was something we showed right before Gauss's time. And which means that it's a prime as an integer polynomial definition. I'll just write this as f divides h implies f divides g or h. This was look at the notes. Okay, so that means that if it's an integer, then it's prime. Now, if f is not, if the degree of f is not an integer, it's greater than 0, so it's not an integer, then we have that it's primitive and irreducible in Qx. Okay, but then, again, if f divides g times h, X. Well, it certainly divides G times H in QX as well. PH QX, but now we are in a PID. We are in a situation where irreducibility implies primeness. Q is rational. The rationals are a field, so QX is a PID. So in particular, F divides G or H in QX. But F is primitive. We just had a proposition we use again that says primitive polynomials dividing integer polynomials in QX means that they also divide them in ZX. I'm on a proposition. F divides H. That's it. Now, if you look back at the proof that a PID is a UFD, you'll see that there are two key things. One is this ability to kind of have this ascending chain condition, which still works in ZX. Just a degree argument, and then the fact that ascending chains kind of stop in integers. And use that irreducibles are prime. You can look over that result and use this proposition that we just did to prove very easily this theorem, which I won't do that, but which is just that ZX is a UFD. Moreover, you can kind of get the unique factorization. There's the form. You can factor into prime integers and prime and irreducible sort of the unique factorization looks like this. This is sort of the result we wanted to get to. This is actually really, really useful in, as I said, when you're working with fields or doing any kind of number theory or any of that stuff. This is a very useful result. And it's, again, it's part of a kind of a larger package, which is kind of a bigger theorem, relies on a little bit more, but not much. And a lot of the methods that we talk about here can be kind of repeated, which is that if R is a UFD, then R of X. We don't quite have all the tools we need to do this. Okay. So now, didn't like that. It was too abstract. Okay. We do something much less abstract. It's kind of enjoyable, kind of pleasant. It's like, hanging out, Thanksgiving turkeys on, play with some mathematical polynomials. You guys do this in your family? Absolutely not. Give it a try this season. Give it a try. See how it goes. There's one thing that'll shut an uncle up. Start talking about math. All right. So here we just want to do kind of things you do, I don't know, elementary school, or what do you want to do? Yep, like middle school, I don't know. First, so Arden starts this section with like a lemma, which is embarrassing for me to write down. I'll do it. This is section 12. It's about like factorizing the, I mean, you have these exercises and they call it algebra. I mean, it always offended me that they call these courses algebra 1. The worst. I'm such a little jerk too, and I mean, still kind of a jerk. I used to like, they have this text, it's 2 books, it's called Basic Algebra 1, and Basic Algebra 2, written by Nathan Jacobson. It's a graduate level text. It's actually a hard graduate level text. It's not one of the easier algebra textbooks. We don't use it here. It's too hard. When I was in high school, I used to go like cafes, that when people did that thing. I would like bring this book, you know. Like I was trying to read through it. It was hard. But you know, people would come up and be like, "Oh, I know algebra." Oh, please sit down and help. And like flip to the chapter. Oh, why is this a UFB? People would really still say, you know, I just don't remember doing this part. You know, I know this. But people would say this. I hate that we call it algebra. Anyway, this is this is algebra. Yeah, what? But arithmetic. Arithmetic. Which the numbers are not simple. You're not actually proving it. You don't really understand the structure. It's like algorithms. I don't know. Algorithmic is, it's not bad. It's good to know how to do this stuff. You should know how to do this. I'm not like trying to say we don't need that as part of our education. I'm just saying algebra is not what there's a big difference between what we call algebra. Same with anything, except calculus. Calculus is calculus. You'll never find a mathematician that says, I'm a professor that works on calculus. Calculus sort of ends. You have analysts. Right? I like them personally. They're good people. That's how I feel about them. You know that. Really. All right. They feel the same way about algebra as I do. Okay, so an integer polynomial, p1 x plus p9 divides x. If that happens, then p1 divides an. I didn't write this down. So b, what is f? F of x. An x. Not, so that's what it is. Divides and oops, p9. I mean, you do this, and I think you do this in middle school. Like when you're trying to factorize. I don't know when you do this. I forgot. And my kids aren't quite old enough. Anyway, you have like a polynomial, and you want to factor it. And you have like a linear polynomial with rationals, and you are with integers, and you want to say, okay, well, this is a leading prism divide this. He tests things out. Okay. Okay, so a primitive does this as well. It's just a root testing. But this is not. Primitive polynomial p1 x plus divides f. Only if negative b. We already actually had this. This follows from the division algorithm, really. You can just, multiply by negative b naught over b1, and then it's like x minus. So it's a root test. You can check and see if you have a root, and then if you have a root, you have a factor, a linear factor. And then this one is kind of something. The rational root harmonic polynomial. F is an integer. And I approve all this just exercises. I don't want to or read the book. Or remember what you did. So here's what this what's kind of fun. This is kind of fun, a fun thing to do in this section. So which is, okay, so we're spending all this time thinking about factoring integer polynomials and rational polynomials. How can we produce irreducibles? Or think of them as the same thing as primes. How do we produce prime polynomials? And how is it possible? We know for integers, we know how to kind of do it. We have this, like this sieve method where we can just say, okay, get rid of all the multiples of 2, get rid of all the multiples of 3, and then the first one where you're not, you have to cross things off the list, 7, 5, 7, so keep on killing multiples until you find the next one. How do you do this with polynomials? And so there is actually a way of producing a lot of irreducible polynomials, rational polynomials. And this is called a technique where you just repeatedly apply this proposition. Okay, so let's suppose we have an integer polynomial. Yeah, I'll write it up. Integer coefficient. And we're going to assume that P is a prime. Prime integer. And P does not divide the leading coefficient. So if f bar of x, which is going to be now polynomials with coefficients in the field with p elements, is irreducible. And so is f. And you can say, I'll say that just generally. It's irreducible as an element of integer or rational. But we know this is sort of not the exact same thing, but up to being primitive, it's the same. I may have an integer factor. I should say it. Actually, I should say that. It's in as a rational. But it may have an integer. What's the proof? Well, it's sort of a contrapositive proof. And you suppose that f is reducible as a rational. Suppose f of x equals to g of x. I'll write all the x's up h of x in x. Well, here I'm going to assume that G and H both have positive degree. Otherwise, I've just got one of these or different. It's reducible. I can assume that both of them have integer coefficients. This is what we got from what we just did in this last section. Assume that this fact, if it's reducible in QX, is reducible in Z. That's okay. Assume that's both in. And furthermore, I can assume that their leading coefficients are both not divisible by P. Why can I assume that? Don't tell me.
I mean, F would be irreducible.
Well,
Or it wouldn't be irreducible.
I'm assuming F is reducible. I'm going to do the contrapositive. So I'm going to assume that F is reducible. That F is reducible, and I'm going to conclude then that this is reducible in FP. So contrapositive is like if I have A implies B, and it's the same thing as saying not B implies not A. The contrapositive. I'm going with that. I'm going with the contrapositive. So what am I assuming for the contrapositive? I'm assuming that F is not irreducible, maybe it's reducible, and I want to conclude that F bar is reducible. That's what I'm assuming. That's why I'm saying, okay, let's suppose that it's reducible. And then I'm going to go there. So if I suppose it's reducible, I still have this presupposition. I have this kind of thing. P does not divide AN. That still stands. That's part of my assumptions. But P does not divide AN. AN is the product of the leading coefficients of these two. If P doesn't divide a product of two numbers, then P doesn't divide either one of those two numbers. Otherwise, it would divide the product. So that's why I can assume this. Okay, so assuming that, we now reduce mod P. But when I reduce mod P, what do I have? I have two positive degree. This is the degree will only change when you reduce mod P if the leading coefficient is divisible by P. If the leading coefficient is divisible by P and you reduce mod P, that term goes to 0. But if it's not divisible by P, then that term does not go to 0. And so it still has the same degree. So these two both have the same degree as before, namely they're both positive degree polynomials. But then this gives you a factorization in F. In particular, so F is reducible. We conclude. And here in F. Very innocuous, but what do we get out of it? We get a lot of irreducible polynomials in QX. So Arden goes on, and this is what you should do over Thanksgiving, only 1 minute, so I want people to. I think it'd be really great if you did this. Just tell me how. So you can still use the sieve method, where you start with, but you do it with polynomials. Let's do it with F2. On irreducibles. Linears are irreducible. Or, these linear kind of polynomials. These are the only 2 degree 1 polynomials. 0. We'll do monics only. I mean, monics mod 2. Okay. So now, then we take products. So we'll take products. We have x squared. We have x times x plus 1, which is x squared plus x. We have x plus 1 squared, which is x squared plus 1. But we're missing one, right? There's one polynomial not on this list. What is it? It's quadratic. A polynomial. X squared plus x plus 1. This is irreducible. In F2. But then that tells us, which you could do just by simple methods, that, you know, like x squared plus, you know, 7x plus 13 is irreducible in QX. Because if I reduce mod 2, I get this. This you can check because you have the quadratic form. You see some rational, you know, some square root, which is not irrational. But you can do this for cubics, quartics. You can get out of that situation where you have any solutions, and you can prove and start producing a bunch of irreducibles. So this is very useful to like extend your rational. I'll see you guys. Actually, I have one more opportunity to get to. Thanksgiving math.
Can I ask you a question about